All right, let's graph some stuff. Let's start off with, I think this is an interesting one. Let's go ahead and start off by graphing x equal to x times the square root of x squared minus 25. Okay. This pen is going to suck for a minute, but it'll get better shortly. So we want to find all the things. I will also point out that this particular function, has a domain restriction. So here we need the insides to be bigger than or equal to 0. So factor this, and usually if you have something nonlinear in your inequality, you want to solve it by factoring. So we're going to factor this, and we're going to say that, okay, number line here, 5, -5. Pick something larger than 5, like 6, positive, positive. Pick something in there, it's negative. Pick something over there, it's positive. And again, this is just to see if the function is defined, right? This isn't going to be increasing, decreasing, increase, right? Because this is the function f. All right, let's just say it's not even the function f, it's the insides of f. And then we want to write them. So I only can get where the insides are positive or 0. So my domain here is everything from -infinity to -5 union 5 to infinity. So it's not even defined between -5 and 5, which means we're not going to find any y-intercepts. So y-intercept, none. Right? X can't be 0, we don't get a y-intercept. X-intercepts, so you set the whole thing equal to 0. We set x times the square root of x squared minus 5 equal to 0. You would normally get x equal to 0, except 0 isn't in the domain. So, right, x equals 0 is nope. And then you get this inside equal to 0, sorry, x squared minus 25. Which means we're going to get x equal to plus or minus 5. So we're going to get x-intercepts at 5 and -5. This graph shouldn't have any asymptotes, right? There's definitely not any vertical asymptotes, because the only way you get the vertical asymptote is if you have like a denominator that's equal to 0 or a logarithm. We have none of those things, no logs, no fractions, no vertical asymptotes. And then horizontal asymptote, we also do not have a horizontal asymptote. To have a horizontal asymptote, you typically have to have some sort of rational function. And that's not entirely true, but the other type of function that has a horizontal asymptote is an exponential function, and we haven't really talked about graphing those yet because we don't talk about that until 16b. So no logs, no fractions, no rational functions, no asymptotes. Okay, great. So we've got kind of nothing so far, right? Here's our graph so far. There's a point there at 5. There's a point there at -5. That's kind of all we have. And then something's going to happen this way and that way. Okay, let's see what we've got. So let's find the derivative stuff. To find the derivative stuff, our function f of x equals x and the square root of x squared. Oh, first of all, it's going to be better if we write this as x squared minus 25 to the 1/2 power. That's just going to be easier to differentiate. Let's write it like that. So, taking the derivative, you can use the product rule. It's going to be 1 times my stuff. I should say 1 times the other part plus x times the derivative of this, which is going to be 1/2 times this inside part to the -1/2 power times the derivative of the inside part, which is 2x. Okay, and this is where it's really, really important to simplify, right? If you're trying to solve this equal to 0 or undefined, it might not be super clear unless you do some work. So I feel like we're not going to get anything. That's okay. Sometimes you don't get a lot of stuff. So from each of these, we can factor out an x squared minus 25 to the -1/2 power. I'm left with an x squared minus 25 to the first right? Because again, if you multiply this back through, this times this would give you a positive 1/2 power. And here I'm left with, let's see, the 2's cancel. I factored this out. I'm left with an x squared. I see that there's a question. Let me see. Oh, okay, sure. Yeah, we can even do that for this problem, Marshall. Yeah, I can talk about that. So yeah, let me finish this first derivative part, and then I'll answer the question that's being asked, which is worthwhile. So let's see. Here we're going to get x squared plus x squared, so 2x squared minus 25 divided by, let's just pick a different number. Oh well, divided by x squared minus 25 to the 1/2 power. And this is equal to 0 when the top is equal to 0. So when 2x squared minus 25 equals 0, so 2x squared equals 25, x squared, so x squared is 25 over 2. So x is the square root of 25 over 2, plus or minus. So here's the thing about this number. 25 over 2 is about like 12 and a half, is 12 and a half. And the square root of 12 and a half is, it's somewhere like, so the square root of 25 over 2 is less than the square root of 12 and a half, which are less than or equal to the square root of 12 and a half, which is equal to, less than or equal to the square root of 16, which is 4. Here's the problem. This number is 4 and negative 4. It's not in the domain. So we have no, well, that's not true. We do have a critical point because although this is not, right, because this is not in the domain, we also have the places where the derivative is undefined. So x equal to 5 and x equal to negative 5. Okay. The interesting thing about that is that if we look at this, so if we look at the number line, 5, negative 5, if we look at the first derivative, if we pick a number larger than 5, like 6, the top is going to be positive, the bottom is going to be positive. If we pick a number like 0, the top is going to be positive and the bottom is going to be undefined because it's going to be a negative number square root. And if we pick a number smaller than negative 5, like negative 6, top is positive, bottom is positive. So here's what we've got. We've got an increasing function and then undefined and then an increasing function. How exciting. Okay, let's go back to the other side because we're still trying the second derivative stuff. So someone asked about how to show that there aren't any horizontal asymptotes. So to find a horizontal asymptote, or to show that there is or is not a horizontal asymptote, you take the limit as x goes to infinity. And if it's a real number, then you have a horizontal asymptote. If you get something that doesn't exist or is a non-real number like infinity, then you don't have a horizontal asymptote. So if you look at the limit as x goes to infinity of x times the square root of x squared minus 25, you're going to get infinity times infinity, which is infinity. If you take the limit as x goes to minus infinity of x times the square root of x squared minus 25, you're going to get negative infinity times infinity, which is negative infinity. So both of these limits being not real numbers, right, not just values, means we do not have any horizontal asymptotes. So yeah, if you have to do that, that's how you do that. Let's go ahead and find the second derivative stuff. I feel like I might have picked one out of the book that's not very interesting. Oh well, sometimes they're not very interesting. Yeah, we can remember their x intercepts are plus or minus 5, I think. So here's our first derivative. 2x squared minus 25 over the square root of x squared minus 25. I believe that's what we had. Yep, that is what we had, except we want to write the bottom as x squared x minus 25 to the 1/2 power. Easier to do it. Now let's find the second derivative. That's going to be the bottom times the derivative of the top, which is 4x, minus the top times the derivative of the bottom, which is 1/2 times our stuff, negative 1/2 times the derivative of our stuff, which is 2x, all over this squared. So x squared minus 25 to the 1 power. Okay, we have to simplify. Yeah, I'm going to erase all this stuff because we found it and there isn't anything there, so we can erase it. So this sure. Why not? So I can still factor out an x squared minus 25 to the negative 1/2. I can also factor out an x. Okay. So from here, I factor out the x, there's still 4, and there's still an x squared minus 25 to the 1. And then from this piece, the 2 and the 1/2 cancel. I factor out the x and the x squared minus 25 to the negative 1/2 power. And I'm left with a minus 2x squared minus 25. All divided by x squared minus 25 to the first power. Okay, bring this down. So we're going to have something over x squared minus 25 to the 3/2 power. And then here we have an x times, let's see what I've got. I've got 4x squared minus 2x squared. So that's going to be a 2x squared. And I've got 4 times negative 25, so negative 100 plus 25. So that's going to be negative 75. Gross. So here's what we get. We get x equal to 0, which is not in the domain, right, from that part there. We get x equal to plus or minus 5, which we know are the endpoints. And then we get this equal to 0. So 2x squared minus 75 equal to 0. 2x squared equal to 75. X squared equal to 75 over 2. So x equals plus or minus the square root of 75 over 2. And 75 divided by 2 is just a little bit bigger than 36. So the square root of that's going to be a little bit bigger than 6. So we get about plus or minus 6, which is in the domain. So we actually do have to check this. Okay, let's see what we've got. Yeah, let's draw the number line up here first. Let's do it over here. I think we can fit this in here. Here's my number line for the second derivative of my function. And I know that I've got these wacky kind of numbers. I've got, here's my negative 5 and 5. This part in here is dead to me, right? Not the domain. We don't look at it at all. And then that there is the negative square root of 75 over 2. And that right there is the positive square root of 75 over 2. So we're going to pick something bigger than that. So go big, right? Pick like 100. Pick 100, positive, positive, positive. Whole thing's positive. You pick something between these two numbers. So something bigger than 5 and less than the square root of 75 over 2. You could actually pick the number 6 because 6 is smaller than this number. So we pick 6, positive. This is going to be negative because you got 2 times 36, which is 72, minus 75, which is negative. And this part's positive. So the whole thing's negative. And then way over here to the left, I'm going to pick like negative 100, negative, positive, positive. Then you pick the number between these two, like negative 6, negative, negative, positive. So here's what we've got. It's concave down, concave up, concave down, concave up. So we have inflection points. These points right here are inflection points. And if you look back at the original function, I don't really think you need to find the y values, but you could. Now I'm curious. If we plug that in, you plug in the square root of 75 over 2, you get the square root of 75 over 2 times the square root of 75 over 2 squared to 75 over 2. I'm going to change this to 50 over 2 to the 1/2 power. So that's going to be the square root of 75 over 2 times 75 minus 50 is 25 over 2. I mean, that's not a terrible number, right? This is going to be the square root of 25 times 3 over 2 times 25 over 2. That's 25 over 2 root 3. Do we need to know this? Probably not. Okay, let's graph the thing. So I do think I feel like I picked kind of a funky example. Sometimes examples are funky. So here's our graph, right? It's starting at 5, -5. And here's what we know. We know that on either side it's increasing. So it's going to be increasing here and increasing to that point there. We also know that we have an inflection point a little bit to the right. So our inflection point over here, right? So maybe like there's 6, there's 7, here's our point, which is the square root of 75 over 2. And so we know that from here to there, it's concave. Which way? It's concave down and then concave up. So it's probably going to do something funky like this. So yeah, it's going to be something kind of like that and then like that. Again, this is not exact. The other side over here is going to kind of look like the reverse of that, actually. It's going to be kind of like, and then it's a weird graph. Are there any specific questions about this one before we do one that's more normal? I'm curious to see what it looks like on Desmos, to see how good a job we did. Take a look real quick. I love the Desmos' website called Desmos, beautiful free math. Okay, let's see here. I'm going to share this with you guys so you can see it as well. So if we graph x times the square root, that's not how you write square root, SQRT. What do we got here? X squared minus 25. So, I mean, my graph kind of underplays it a little bit, but right. So yeah, I mean, my graph doesn't look exactly like their graph, but it's the same idea, right? It's just their graph, my graph is a little more, I don't know, it's a little less extreme, but right, we're still seeing the concave downness. You can kind of see that, right? If you start here and you go this way, it is concave down, and then at some point here-ish, I don't know, somewhere like here, and maybe like somewhere around here, the concavity changes. It's very slight though. The other thing I should point out with my graph, just so you guys are aware, is that when I was graphing this, I did take care to make sure that the at the 0.5 there, that the tangent line is vertical, because if you look back at that, I think I erased the first node. Yeah, so if you look back at the first derivative, right, the first derivative was undefined at 5, meaning that you're going to have a vertical tangent line. Sure. Yeah. So can I do an example of finding all of this for f of x based on a weird looking graph for f prime of x? I think so. Let's see. I bet there's some examples in this book that might be helpful. Let me see. I just don't want to make something up that's kind of crazy. Not good examples in here. Let's see. You know what? Actually, I have. Let me look here. Sorry, finding an example of that kind of question is a little bit harder. No, that's sure. Maybe that's it. No, I don't want that. And so just to be absolutely clear, right? You're being great to the person asking me the question. There was no equation, just a graph, and they gave you the graph of the derivative, right? Okay. Just trying to find a good example because they don't. Yeah. Let me look back real quick here. Why don't you want to give me good examples, textbook? I'd like to give you guys something that's not super crazy that I just make up, because it might it might not turn out well. But I'm not seeing, yeah, I'm not seeing that. Okay, fine. I'll just need something. So, yeah. Well, I'm going to start off with something relatively easy, and then maybe we'll try a hard one. So let's say we were given, this is the graph of our derivative. I'm going fairly easy here. And I don't know if any points were labeled, but I'm going to label a few things just so we can have them here. So on my derivative, this is the point. I'm going to call this 0, -4. This is 3, 0. This is -3, 0. These might not actually be super helpful. So I want to graph the original function. So here's what we know. We know that for this function, I should say, I know that between -3 and 3, in fact, you know what's actually probably a really good idea that I just thought of would be to make the sign chart. So, right, if I make the sign chart for the first derivative, I can see that the sign is going to change at -3 and at +3. So over here, the first derivative is negative. Sorry, positive, holy smokes. Between -3 and 3, the first derivative has negative values. And bigger than 3, the first derivative has positive values. So that means we know that from -3 to -3, our function should be increasing. From -3 to 3, decreasing. From 3 to infinity, increasing. So that's going to help us graph it. So this actually is, I think, a really good idea to at least look at what's happening with our function. So when you look at -3, 3, I don't exactly know what the values are, but I do know that before I get to -3, the function should be increasing, and after -3 to 3, it should be decreasing, and then it's going to be increasing. I want to say there's something else I should say here, and that's that. So if we look at this derivative again, just for a minute before I start graphing this thing, I can also see that my derivative itself, right? So if you look at this, the derivative is the derivative is decreasing and then increasing, right? The derivative started off really positive, got negative, got lesser, 0, negative, more negative, super negative, and then right there, it stopped getting smaller, it started getting bigger. So what you can say here is that we're going to have an inflection point when x equals 0. And the reason we have an inflection point is because an inflection point is where the derivative changes the direction it's changed. Like the derivative goes from decreasing to increasing or increasing to decreasing. Another way to say that, right, is if you look at this, right, if you think about the derivative of this, well, the derivative of the first derivative is the second derivative. And if you look at the sign chart of the second derivative, well, my first derivative is decreasing from -infinity to 0. That means my second derivative is negative. And my first derivative is increasing from 0 to infinity. That means my second derivative is positive. Right? If a function is increasing, its derivative is positive. So if the first derivative is increasing, its derivative, the second derivative, is positive. Okay, so I think that's going to help me. So now I'm going to try and graph it. So I know I'm going to have a relative maximum at -3. So maybe right there. So I know it's going to do this kind of deal. And then I have a relative minimum of +3, maybe right there. And then we can try and graph it to be like this. And then right there, we're going to change concavity. Like that. So that's how we can do it for at least this one. But now let's try to do something a little bit funkier. But so here's kind of my intuition. From the graph of the first derivative, we can make a sign chart for both the first derivative and the second derivative, which is going to tell us where we have relative extrema, whether it's increasing, decreasing. It's also going to tell us whether the concavity might change. So let's try something a little bit more complicated. Let's see here. For a second. We'll try something wacky. So let's say we had something that looked like this. I don't really know what kind of thing your teacher gave you, but I'll just try to make something up here. So let's say we had something that looks like this, and then from here to here, it's going to be that. From here to here, it might. Sure. Sorry, I'm trying to make up something that's going to be interesting here. Okay. Here's the graph of our derivative. This looks terrible. I can still make a sign chart. So, let's label these points. I'm guessing you probably weren't given numbers. Let's call this A, this B, this C. Or we'll label it. We'll label whatever we need to as we go. So on our first derivative number line, we have these. Let's see. So from negative infinity to A, clearly negative. Oh, I think I might actually need this point here. B. So I might have picked the wrong points. That's okay. So on my first derivative number line, I really just care about the sign. So I actually care about. Yeah. Sorry, I called them the wrong thing. So let's rename this just 1 second. Let's say we have A, B, C, D, E, and F. And on my first derivative number line, I really only want the places where the sign changes. So I want B, D, and E. And then to the left of to the left of B, the derivative is negative because it's below the x-axis. So my function is decreasing. I know from B to D, the derivative is positive. So the function is increasing. And from D to E, the derivative is negative, decreasing. And from E to everywhere, it is increasing. A couple other things we actually also know, specifically in this region here, if the derivative is a constant, then we know that the function is a straight line. So we know that maybe like if you just want to look over here, right, at A, the sign's not changing, but over here it's going to be a straight line with negative slope. And same thing after we get to the point F. Right, after the point F, right, it's still going to be a positive slope, but it's going to be a straight line with positive slope. So we could maybe try and graph this right now. I probably should have tried to line this up. Yeah, I can. Yeah, fine. We'll try drawing this here and see what we can get. So way over here, we know it's going to be a straight line with a negative slope. So maybe it looks like. Nah, I don't have enough room. Yeah. Let me move this over here real quick. Sorry, should have done this. Okay, decreasing. Okay. Here. So up until we get to this point right here, it's not a vertical asymptote, I'm just saying what's happening. We have a line with a negative slope that's a constant. Maybe something that does this. And then from here to B, the slope gets less negative, right? the slope is negative, and then it's going to kind of gradually stop being negative and maybe reach some minimum, right? Because at B, we should have a relative minimum because it goes from decreasing to increasing. And then from B to D, sorry, yeah, from here to here, it's going to be increasing, right? It's going to, yeah, sorry. Something like that. And then from D to E, it's going to decrease. Right, so we have a relative maximum here. And then from D to E, it's going to decrease. Now, the thing is, it can't just decrease like that, because we're not saying that the derivative is a constant. We're saying, okay, at first, the derivative is just a little bit negative. So the rate of decrease is kind of small. So, right, maybe it kind of goes like that. But then as you move this way, the derivative is as negative as it gets. So like right there, the slope of the slope is as negative as it can be. And then after that point, you have to kind of become less negative. So maybe you're doing like this. And then from E to F, the slope is positive. Again, it starts off a little bit positive, gets to be more positive. Now, what's happening at F? Oh, the function's undefined. Sorry, I didn't give myself a whole lot of room here. Or sorry, the derivative is undefined. So if the derivative is undefined at F, that means we might have something like this, where the tangent line is vertical. And then after that, we have something like that. So hopefully this kind of helps with the question that was asked. I mean, it's always kind of a process to be like, okay, well, the derivative is negative, the function is decreasing. The derivative is positive, the function is increasing. But that's really most of what I think about when I'm trying to remake the graph from the graph of the derivative. So if I erase these a little bit, kind of give some separation between the two graphs. You can kind of see, oh yeah, there's my graph, right? Derivative is negative and constant. Then the derivative is getting less negative, right? The slope is negative, less negative, less negative, less negative, less negative, 0. Slope is positive, 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 positive. And then less positive, less positive, less positive, less positive. And then the slope is slightly negative, slightly negative, slightly negative, most negative. And then less negative, less negative, less negative, less negative, 0. And then slightly positive, very positive, super positive. Maybe there should be some sort of asymptote here. I'm not actually sure about that. Yeah. And then after that, it's constant. I feel like maybe what should actually be happening, and I know I didn't really line these up very well. Let me fix that a little bit. Let me give myself a little bit more room. So what I think actually should be happening here, we have like a vertical asymptote here. Yeah, maybe not. I don't know. No, I don't think we get a vertical asymptote because, sorry, 1 second. Let me think about what's happening here. So we've got a slope here, and the slope is, sorry, the derivative is just some positive number, right? It's getting closer and closer to, let's pretend this is 5 for a minute, just to give it a number. So when we get to that point there, so right there, the slope should be something like positive 5, right? So the slope of the tangent line, whatever it is, increased from 0 to 5. But then at that point, well, then after that, the slope is just 5 after that. So then it just continues on in that same, yeah. So I didn't draw this very well, but, right? So basically what's happening is you're coming up to a point, and then when you get that point, the slope just continues being constant in that same direction. So yeah. That's what that looks like. Okay. Yeah, those questions can be challenging for sure. Let's look at a few more graphing problems. If you want to see another one of those, I can try and do another one. If you have a specific example that you wanted to email me, I could look at that and then do something that's maybe a little more well thought out. Let's look at some more graphing stuff. Yeah, let's look at that. Let's look at graphing f of x equal to, this is, yeah, sure, x squared minus 6x plus 12 over x minus 4. Find all the things. So thing 1, y-intercept, so x equal to 0, you're going to get 12 over negative 4, which is negative 3. Thing 2, x-intercept, set the top equal to 0, x squared minus 6x plus 12 equal to 0. And does this factor? Good question. I don't think it does. Yeah, what a terrible example. So we look for the x-intercepts by using the quadratic formula. So x is going to equal negative b plus or minus the square root of 36 minus 4 times 1 times 12 all over 2 times 1. No solutions. 36 minus 48 is negative. So this has, right, this is imaginary or complex. So no x-intercepts. Right, if your discriminant is negative, you have no real solutions. Okay, let's look for vertical asymptotes. That should be easy enough. Vertical asymptote, we're going to get the denominator equal to 0, so x equal to 4. Horizontal asymptotes, there aren't any. You can show that there are no horizontal asymptotes again by taking the limit. The limit as x goes to infinity. If the degree on top is larger than the degree on the bottom, I don't know how much work she wants you to show. So I'm used to saying this is infinity just because the top degree is bigger than the bottom, but you can divide everything by the highest power in the denominator. So if you divide everything by x, you get the limit as x goes to infinity of x minus 6 plus 12 over x all over 1 minus 4 over x. This goes to infinity minus 6 plus 0 over 1 minus 0. So infinity minus 6 over 1, that's infinity. And then if you're going to negative infinity, you would get negative infinity. So the same limit as x goes to negative infinity of this same expression. Right, now you get negative infinity minus 6 plus 0 over 1 minus 0. That's going to be negative infinity. So we don't have a horizontal asymptote. But since the degree on top is 1 larger than the degree on the bottom, we do have a slant asymptote, and we should find it. So to find the slant asymptote, you just do the polynomial division. So it's going to be x minus 4 divided into x squared minus 6x plus 12. Let's see, what do you multiply by x to get x squared? You multiply x times x is x squared, x times negative 4 is minus 4x. We subtract x squared minus x squared is 0. Negative 6x minus negative 4x is negative 6x plus 4x, which is negative 2x plus 12. And then what do you multiply by x to get negative 2x? It's negative 2, and you stop right there. You don't have to do anything else. That's your slant asymptote. Okay, let's find the first root of things. Again, if there's something you really want to see, just ask. I'll try to make it happen. So our function was x squared minus 6x plus 12 over x minus 4. Our first derivative is going to be, should switch pens. Should give this pen a break. First derivative is going to be the bottom times the derivative of the top, which is 2x minus 6, minus the top times the derivative of the bottom, which is 1, all over the denominator squared. Simplifying, let's see, multiplying this out, I get a 2x squared minus 8x minus 6x is minus 14x. Minus 14 is minus 6 is plus 24. And then distributing the minus sign, minus x squared plus 6x minus 12, all divided by x minus 4 quantity squared. Simplifying the top, 2x squared minus x squared is x squared. Minus 14x plus 6x is minus 8x. And 24 minus 12 is 12. And this does factor. It factors as x minus 6 times x minus 2, all divided by x minus 4 squared. So our critical values are x equal to 6 and x equal to 2. And even though 4 isn't a critical value, it's still an important point we include in the number line. So our pseudo-critical value is x equal to 4. We know it's not a real critical value because we know we have a vertical asymptote at that place. So looking at the number line for our first derivative stuff, so 2, 4, and 6, make something larger than 6, like 7, positive, positive, positive. Between 4 and 6, like 5, negative, positive, positive. Between 2 and 4, like 3, negative, 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 positive, positive. And then finally, less than 2, like 1 or 0, negative, negative, still positive, so the whole thing's positive. My function's increasing, decreasing, decreasing, increasing. So it looks like we have a relative maximum at x equal to 2. And if we want, we can find the y value by plugging into. The y value is going to be 4 minus 12 plus 12 over negative 2. So 4 over negative 2 is negative 2. X, y. And then we have a relative minimum at 6, comma, whatever f of 6 is. Let's see, it's 36 minus 36 plus 12 over 6 minus 4. That's going to be 12 over 2, which is 6. Okay. So at this point, you can probably start graphing the graph, even though we haven't found the second derivative stuff yet. Here's what we've got. We've got our y-intercept at -3. We've got a relative maximum at 2, -2. And we've got a relative minimum at 6, 6. We also have a vertical asymptote at x equal to 4. We have a slant asymptote at y equal to x minus 2, was it? Yeah, x minus 2. X minus 2 goes to the point -2 and 2, so it's going like this. And then we can use the first derivative sign chart to graph the thing, right? We see it's going to be increasing until you get to this point, decreasing afterwards. And then after the asymptote, it's going to be decreasing until you get to that point and increasing afterwards. So it's going to look like this. And it looks like the second derivative is going to tell us that it's concave down over here and concave up over here. But we should probably still do it. It's kind of a pain. So let's look at this first derivative here and take the derivative of that. Yeah, a lot of times, especially with rational functions, if you have the first derivative information and all the other stuff, it's kind of enough. So if my first derivative is x squared minus 8x plus 12 over x minus 4 squared, my second derivative is going to be, I bet it's going to be a constant over x minus 4 cubed. That's my guess. Let's double check though. So let's see, derivative of the top is 2x minus 8 times the bottom minus the top, x squared minus 8x plus 12 times the derivative of the bottom, which is 2 times x minus 4, all divided by x minus 4 to the 4th. Okay, here's something kind of great. 2x minus 8 and 2 times x minus 4 are exactly the same, so we can just factor those out. This is going to be 2 times x minus 4 times x minus 4 squared. which is x squared minus 8x plus 16, minus this, so minus x squared plus 8x minus 12, all divided by x minus 4 to the fourth. One of those cancels with one of those. This and this cancel, this and this cancel. 16 minus 12 is 4. So I end up with 2 times 4, which is 8 over x minus 4 cubed. So if we make the sign term in the second derivative, the only critical number is 4. And we see that the second derivative is positive over here, negative over here, so it's concave down, concave up. We don't have an inflection point at 4 because 4 isn't actually a critical value because it's not in the domain of the original function. Whew. Not a bad question. Okay, let's switch gears and do some optimization. Unless you want to see more graphing. Sure. Let's go ahead and do some optimization. I'm kind of looking at the previous homework optimization problems from Wynn's class for inspiration here. I'm going to change some of the numbers. I mean, I guess it doesn't really matter because you guys already printed this homework out. So let's look at this one. An open box, meaning a box with no top, is to be made from a rectangular piece of cardboard, which is 16 by 24 inches, by cutting equal squares from the corners. So we've got a 16 by 24 piece of cardboard, and we're going to cut out squares, equal dimension squares, from each of the corners. And then we're going to fold up the sides to make a box, right? This is going to give us a box. It's going to look like, you know, right, there's our open top box. And we don't know how big these squares are. So we're going to label them with whatever variable you want. I'm going to call it x. That's x, right? We could label them all, seems kind of unnecessary. But what is important to know is that this length here, the length, which is this length here, that's going to be 24 minus 2 x's. And this length here, which is this length here, is going to be 16 minus 2x. And then this height here is going to be just x. So the thing we're trying to maximize is that how much volume, so I should read the whole question, apologies. Right, find the size of the square, which gives the box of the largest volume. So we're trying to find x, find the x value that maximizes the volume. Okay, well, the nice thing about this particular problem is we don't even have to find a constraint. It's already kind of been found in doing the setup. So the volume that we're trying to maximize is just base times width times height. So 24 minus 2x times 16 minus 2x times x. And usually I would multiply this out, but I feel like it might be easier to not and just use the triple product rule. I don't know. Let me show you. So if we want to find the derivative here, right, because we're trying to find the critical values, the triple product rule says you can differentiate each part and multiply by the other two parts. So it's the derivative of this, which is -2, times the other two parts, 16 minus 2x times x. And then the derivative of this, which is also -2 times this part times this part. Sorry, it's going in hot. All right, there we go. So -2 times 24 minus 2x times x. And then finally, the derivative of this part, which is 1 times this times this. I don't know, this might not really be less work. This does not feel like less work to me. So the other thing we could do is we could just multiply this out and say, okay, b is going to be, let's see, this times this is 24 times 16. 24 times 16 is a number I should know, but don't know off the top of my head right now. Yeah, what is it? It's 384. Yeah, 384. And then minus 32x minus 48x, so it's going to be minus 32 minus 48 is going to be minus 80x, and then plus 4x squared times x. So then the volume would be, and then v prime would be, all right, it's getting to be tedious, 384x minus 80x squared plus 4x cubed. So the derivative would be 384 minus 160x plus 12x squared. That's probably less work to multiply that first and then take the derivative as opposed to trying to use the triple product rule. So we're setting this equal to 0. So we're going to solve this. You could probably factors, right? Often people write these problems so that they factor, or you could just jump straight to the quadratic equation. I would probably try factoring it. I would probably actually first try seeing if there's any common factors. It definitely looks like 4 is a factor of everything. Let's see. So we've got 12x squared minus 160x plus 384, 0. You divide everything by 4, you get a 3x squared minus 40x. And 384 divided by 4 is going to be, let's see, 4 goes into 38 9 times. 9 times 4 is 36. 2 remainder, 24, 6 times. Still not fun. Yeah, does that factor? I don't know. Probably. You could try, I don't know, do we want to try and factor it? I mean, so let's see. So 3 times 96 is 288. So you're looking for numbers that multiply to 288 and add up to 40, negative 40. Let's see. So we could do 2 and 144, or 4 and 72, or 8 and 36. So it seems like we're getting close. I think you could do, let's see, 36 is 9 times 4. I guess, yeah, we're very close, but not quite. Sorry, there's a lot of ways to do this. I think the quadratic formula is our friend. Right, so if you're factoring something or trying to factor something and you're like, this seems too hard and it's quadratic, just use the quadratic formula. So we're going to get x equal to negative b, so 40 plus or minus the square root of negative b squared, so 40 squared is 1600 minus 4 times 3 times 96, all divided by 2 times 3. So that's going to be 40 plus or minus the square root of, let's see, 4 times 3 times 96. Let's just get up the calculator. 1152. So 1600 minus 1152, all over 6. Let's see. That's 448. And that does not have a nice square root. So it's 40 plus or minus the square root of 448 all over 6. So we end up getting, yeah, that's gross. So the question is, which is it? Is it 40 plus or is it 40 minus? Well, the square root of 448 is about like 22, I think. Holy smokes. Yes, okay. Oh. I hate when I type in square root of 448. It's like, it's the square root of 448. Yes, I know that. It's approximately 21.1. So here's what we've got. We've got that our answer is approximately 40 plus or minus 21 over 6. Let's just round that up to 22. So 40 plus 21 is either 61 over 6, which is about 10, or 40 minus 21 is 19 over 6, which is about 3. And one of those doesn't work, right? If your answer is about 10, 24 minus 2 times 10, well, that's okay, that's 4. 16 minus 2 times 10, that's not okay, that's negative 4. So typically when you're finding a critical value in some sort of real world situation, like this real world situation, right? Oftentimes if you get more than one critical value, one of them is going to be nonsensical. It's going to give you like a negative length. So this, well, I should really say, so our actual answer is 40 minus the square root of 448 all over 6. Kind of gross. Let's look at another example. Let me pick an example that I have. Sure. Let's look at that one. Yeah, okay. Let me see. What is the volume? No, not volume. Find the dimensions of the largest by volume cone, sorry, not cone, cylinder that can be, yeah, sure, inscribed in a sphere of radius 6. All right, so let's draw the picture. So here's our sphere, radius is 6, and our pen, sure. Here is our cylinder. We want to find the dimensions of the cylinder. So the cylinder has dimensions, right? Radius and height. We want to find the radius and the height that make the cylinder have the most volume. Okay. It might help to draw a less nice picture, actually, meaning instead of drawing a sphere and a cylinder, let's just draw the circle and the cylinder, which is really just kind of like a rectangle. And I want to know the radius and the height of the cylinder. Okay, so I'm trying to maximize the volume of my cylinder. Well, I know the equation for the volume of a cylinder. The volume of a cylinder is pi times the radius squared times the height. But we also have to have a constraint, right? I should really say we're trying to maximize a thing that's a function of 2 variables. We need it to be a function of 1 variable. So we need a constraint. And the constraint here, well, I mean, in words, the constraint is that the cylinder is inscribed or stuck inside the sphere, right? It can't have dimensions that make it stick out of the sphere. So typically the way this is thought of is we know that the corner of the cylinder, the corner of the rectangle here, should touch the sphere, right? If you want it to be the biggest volume in the sphere, you want to have your cylinder touching the corner, the corner of the cylinder touching the sphere. Well, we can draw something, right? We know that from the center to the sphere, that's the radius, which is 6. So we can actually write an equation, and there's 2 different ways to do it. I prefer to do it this way, where you say, well, if this is 6, then the diameter is the whole length of 12, and I can use the Pythagorean theorem and say, hey, look, I've got a right triangle where the height is the height, the base is 2 times the radius, and this length is 12. So that the Pythagorean theorem says, oh, I've got 2r squared plus h squared equals 12 squared. I will mention, some people do it a different way, and they use the smaller triangle that looks like this. And they say, okay, well, that's r squared plus h over 2 squared equals a 6 squared. They're really the same equation, just slightly different. They give you the same result. I tend to prefer to use the one that doesn't introduce fractions if I can help it. All right. So here's an interesting question. Do we want to solve for r, or do we want to solve for h? Well, you might incorrectly guess h. You might guess h because you're like, well, James, clearly it's h, because it's easier to plug back in for h, right? You don't have to square it. And normally I would say you would be 100% correct. But in this particular example, solving for h means we're going to have a square root, right? If I solve for h, you're going to get h squared equal to 144 minus 2r squared is 4 times r squared. And then h would be the square root of 144 minus 4r squared. And you plug that in there, and then you'd have your function would be pi times r squared times this, and taking the derivative would be a giant pain in the butt. In this case, we make an observation. We say, hey, look, my equation already has an r squared in it. So if I solve this for, well, really I can just stop at r squared. I can just plug that in for r squared. Here's what I mean. We can say that 4r squared equals 144 minus h squared. And then multiplying both sides by 1/4, r squared is 1/4 times 144 minus h squared. You could square root both sides, but you don't really have to, because you're going to end up plugging that in right there. We can also write it, right? R is going to be the square root of all this, which is 1/2 times the square root of 144 minus h squared. But then when you plug that back in for r, you're going to square it, and you're going to get 1/4 times 144 minus h squared. So if you notice that your constraint has things squared in it, and the thing you're trying to maximize has one of those things squared already, it is often the right choice to actually solve for that one, so that you can plug it back in and not have a big old mess. I think we're done with this picture. Here's what we can do now. We can say, okay, my volume is pi times r squared, which is 1/4 times 144 minus h squared times h. And then we can multiply that out. My volume is just pi over 4 times 144 minus h squared times h is 144h minus h cubed. Take the derivative. Constant hangs out. Derivative of 144h minus h cubed is 144 minus 3h squared. Set that equal to 0. So let's see. I'm going to say 3h squared equals 144. H squared equals, let's see, 144 divided by 3 is some number. 48? Yeah, it's 48. And so then h is going to be the square root of 48. Or if you prefer, that's going to be 4 times the square root of 3. All right. We can find r. So to find r, you do have to actually, right? You do have to solve for r. So r would be this 1/2 the square root of 144 minus h squared is just 48. So that's going to be 1/2 the square root of 96. Okay, the only other question I want to address is, does this actually give us a maximum volume? So one way, probably the easiest way to check, is to use the second derivative test here. I take the second derivative of my volume equation. you're going to get v double prime equal to, let's see, pi over 4 times 0 minus 6h. And if you plug in any positive number for h, you're going to get a negative second derivative, which means it's concave down, which means you have a maximum. Alternatively, you could say that, well, if this is my volume equation, if you think back to the original kind of picture, right, there are some constraints. Specifically, the height has to be bigger than or equal to 0, or you can have a negative height. And the height has to be less than or equal to 12, right? Because the radius of the circle is 6. The longest height you could have would be, I mean, it'd be stupid, right? It would be a no volume thing, but you could have a cylinder that had no radius and a height of 12. Okay, but then we can do the thing where we say we use the extreme value theorem and say, well, I know that if the height's 0, the volume is 0. If the height's 12, the volume is also 0, right? Because here's my equation. If you plug in 0, you get 0. If you plug in 12, you get 0. And then the only other critical value between 0 and 12 is the one we just found. And since when you plug in that, I don't know what you get for the volume, but I do know that when you plug in the square root of 48, you have to get something that's positive. That has to be the maximum, right? We know that a function attains its absolute maximum somewhere on the interval if it's a closed interval and it's a continuous function, which we have here. So since it's not a max there, it's not a max there, it's got to be a maximum at the critical value between the two endpoints. Okay. Let's see, what else can I throw at you guys in the last 7 minutes here? Yeah. One more. Similar but different problem. What is the, find the area, find the area of the largest rectangle that can be inscribed in a semicircle of radius, let's go 10. So let's draw a picture. So here's our semicircle. Radius is 10. And I want to find the area of the largest rectangle. Notice we didn't ask for the dimensions, we actually asked for the area. Okay. So I'm going to draw some rectangle. And I want to find the area of this rectangle. Okay. Typically, for this sort of problem, we're going to say, well, this corner of the rectangle, I don't know where it is, right? I know it's on the circle. I'm going to call it the point x comma y, because I've gone over x and I've gone up y. Okay, so I'm trying to maximize the area. So I'm going to maximize the area, which is equal to, well, it's not x times y, because that's just this half of the rectangle. It's 2x times y. Okay, so now we have to find a constraint. Our constraint here is that, again, just like in the previous problem, when you said the inscribed in something else, the corner of your figure should be on the thing it's inscribed in. So that point xy should actually be on this semicircle of radius 10, which we know the equation for. Right? We know the equation for a circle of radius 10 centered to the origin is x squared plus y squared equals 10 squared. So we solve for y, we get y squared equal to 100 minus x squared. we get y equal to the square root of 100 minus x squared. And we're also making the assumption, right, that this point is in the first quadrant, right? We're not letting it be over here, so we know that x should be between the 0 and 10. Okay. So now we can write our equation because we know that y equals the square root of 100 minus x squared. So then our area is going to be 2 times x times the square root of 100 minus x squared. Or if you prefer, 2 times x times 100 minus x squared to the 1/2 power. Okay, we got to find critical values. Let's take the derivative. That's going to be 2 times your stuff, right? Derivative of 2x is 2 times the other piece plus 2x times the derivative of this is a little bit complicated, right? It's going to be 1/2 times 100 minus x squared to the negative 1/2 times the derivative of the inside, which is negative 2x. Okay. Let's see. We can cancel a 2 here and a 2 here. And then we're going to factor out. So we're going to factor out, let's see, 100 minus x squared to the negative 1/2 and also a 2. So a 2 and 100 minus x squared to the negative 1/2. So I'm left with here, I don't have a 2 because I factored it out, but I do have 100 minus x squared to the positive 1. And then here, I factored out this 2 and this 100 minus x squared to the negative 1/2, but I'm left with an x times a negative x, so a negative x squared. Let's see. So here's what we've got. We've got this in the numerator, so 100 minus 2x squared over, sorry, don't forget the 2 out in front as well, over 100 minus x squared to the positive 1/2 power. We're going to set this equal to 0. Or undefined. So undefined, you get x equal to plus or minus 10, but really x should be between 0 and 10, so we're going to say x equals to 10. And then we're also going to get 100 minus 2x squared equal to 0. So that's going to be 2x squared equal to 100, x squared equal to 50, x equal to the square root of 50. Okay, so is this going to give me a maximum? Yes, right? They ask you to find the maximum. You're going to find the maximum. Right, that's almost always the case, right? If they say find the thing that maximizes it, then the thing you find is going to get to the maximum. But if you want to check, you can say, okay, well, the area, right? So the area function as a function of x, which is that right there, has a domain, an explicit domain from 0 to 10, right? We said x had to be between 0 and 10. And then we can see that, okay, well, if you plug in 0, you're going to get 0. If you plug in 10, you're going to get 0. So you're going to get the maximum volume when you plug in something that makes it not 0. Plug in 50, you're going to get 2 times the square root of 50 times the square root of 100 minus the square root of 50 squared. And that's definitely positive. In fact, we should find it because the question asks to find the area. So that's 2 times the square root of 50 times the square root of 100 minus 50. So that's going to be, oh, look, that's actually nice. It's 2 square root of 50 times square root of 50, which is 2 times 50, which is 100. So the biggest rectangle that you can find in a circle of radius 10 has an area of 100.